Hello, hello. Can you guys hear me? Good evening, everyone. Sorry, this broadcast had to come much later at night. We planned it we moved it to 8 p.m., but I understood that our Muslim peers, they're in their Ramadan, and they make their prayers about 8 or so. So we got request and we moved it to 9 p.m. It's coming quite late. Quite sorry about that. Please, if you can hear me, can you just indicate in the comment section, just so I know? Yes, I'm waiting to. Okay, Aminu Sabiu say yes, they can hear me. Okay, good evening, everyone. Once more, Umar Lawai from Guso, Zamfara State, Abubakar Musa Dankara. Yeah, we can see you. Justice, okay, meme from Aba, Oka Mem or something. Oka Meme, yeah, Oka Meme Justice from Aba. Sash Hour from Enugu. Sani Iliasu from Jigawa State. Tuko Bature from, moving fast. I think I missed Tuko Bature. Jigawa State is Tuko Balarabe, sorry. Wasiu Ibrahim, hello Wasiu. Oh no, Samuel, yes. You've confirmed I can hear you, thank you. Haruna Dangabas, I know this name very well. Hi Dangabas, how are you? Good to see you again, Dangabas. Oh no, Samuel from Abia. Bello Sani from Zamfara State, Mohammed Gigi Yunusa. Yunusa is from Borno State. And yeah, I've seen Ono somewhere from Abia State. Owasiu Ibrahim from KB State. T Ghana Learning and Entertainment from Jigawa State. Aminu Ibrahim Yobe. Ono somewhere, yeah, I know you from Abia State. Yeah, Sani Ibrahim Bello from Kaduna State. Suleiman Bala Mohammed. Hello, Suleiman. Chidubem Obasi, Olajide Tafik. Okay. Sanisu Ibrahim from Kano State. Idris Jibril from Kano State. Good to see all of you. Let me look at the people on Zoom. I have Husseini Mohammed from Potiskum. Ela Peter Ejolim from FCT Abuja, Paul Omol from Abuja, Isabella Meshi from Port Harcourt, Alphonsus Ikome from Edo State, Hassan Bello from Kwara State, yeah, Yusuf Musa from Kano. Good, seeing someone from Kano on the Zoom channel, nice. Udebuna Michael Ikechukwu from River State. Most people on Zoom seem to be from either Abuja or Lagos or Leo Nazo from Lagos. And back here again on my on the YouTube channel is we have Abubakar Mustafa from Maiduguri. Egwem Julius from Kano. Nice. Julius Egwemi from Kano. Amos Samuel, Oyo State. Mohammed Adamu, Niger State. Abdul Kader Lebaran, Gombe State. Adamu Ibrahim from Zamfara. Sabiu Usman. Yeah, it's very diverse. Yeah, I can see people from different Gombe are representing here too. Gombe State again. Okay, yeah, Sabu Ishak, I can see you from Gombe State. Muhammad Adamu, Niger State. Okay, thank you, everyone. Thanks for joining. We'll go right into it because it's late already, so you guys can, get back to what you have to do at night. So we are resuming our routine live sessions. As you already know, we opened up all the courses simultaneously. The hash function, the Merkle trees, they're all running, even the Bitcoin infrastructure, they're running in parallel. So like the hash function, sorry, I'm not sure why my power went off. 1 minute, please. Oh, I have to turn on the inverter. It seems, yeah, you can't see me, but you can hear my voice, I guess. So all the courses are running in parallel, something like the hash function. By April 10th, it will be ending. So the plan is we should have at least 2 sessions every week. So today is Tuesday already. We're having this on Tuesday. We'll probably have another one either Thursday or Saturday. I think Thursday might be ideal. We might have another one Thursday, if possible, another one Saturday. So we'll have live sessions, more often from now, so that everyone will have the opportunity to catch up. It's a lot going on. And for those people that doesn't have computer science background or they've not been coding before, some of the things we are treating now are purely computer science things like hash functions. So it requires us to talk about it, help you navigate through that. And that's what we're trying to do. So going forward, we'll be having these classes. I'll try to work out time that is very good. I was thinking 8 p.m., but the Ramadan, people doing Ramadan, they make their prayer. So I'll have Harrison talk with your mentors, and they should come up with a time that is ideal. I'll, change my schedule to suit into that time. Okay, let's get right on. I'm going to stop sharing now so I can share. Let me stop sharing this so I can share. I guess I'll just share my entire screen so I don't have to keep jumping from. So stop share. Start a new one. Share my desktop. Okay, just share my desktop. So, for instance, that. Yeah. So this is hash function part 1. I intend to do this in 2 series. So we'll have part 1, we'll have part 2. And the part 2 will be the concluding part of this so that we can move on to other topics. All right. So what is a hash function? A hash function is a mathematical process that maps a bit string of any length to a bit string of a defined length. Well, those are computer science jargon. Or just in a simple math sentence. So a function, we did JavaScript, we did Golang, so we understood what a function is, right? So it just a function is some piece of code you write. It takes an input, you give it an input. Within the code, it does all kind of manipulation you want it to do, and it gives you the output. So to the guy using the function, he doesn't know what goes into it. All he knows is that, give an instance, you get a function that converts lowercase to uppercase. So you get a bunch of data, maybe it could be name, people name, you want everything to become uppercase. So you pass into the function. Within the function, whoever wrote the function have written, because every single alphabet maps into it's an ASCII code. So it maps into a particular number, right? So whoever wrote this thing knows about this. It plays around with the numbers, do this minus that, know where it gets into. So whatever alphabet you give it, it look at what number it is. Based on that, it finds out the relative position of that, right? And you find out the uppercase value for it. Because you have the lowercase a, for example, you have the uppercase a. They have different values. So within this, it manipulates that and turns it to uppercase, right? Then, of course, teach everything back. You don't see what's going on. All you see is an output. That's your output is uppercase letter, all of them. So now that's what a function is. So a hash function is also a function, but what it does, you pass any data to it. Let's look at the image. They are the GIF image, right? So you have a plain text. You type whatever it is. You pass into your hash function. It produces a string with that's a defined length. No matter how large your document is, you might give it a page. A novel, some novel can be 100 pages, 250 pages long, right? Let's say you have your soft copy of that novel, and it reads everything inside that novel. It brings out a fixed length, okay, of bytes. You give it another, maybe a page, all right? It runs that, also give you a fixed length. So that's what it does. But that fixed length that it brings out for you is what we call the fingerprint, or the checksum, or the digest. You can use this word interchangeably. So what a hash function does is it gets a plain text received in the image, pass through the hash function, and it comes out with a defined length. Depending on what you're using. For example, you're using the SHA-256, we'll see that as we go along the course, right? It will give you a fixed length. The output will be 256 bits. Yeah, bits. That's what we produce for you, irrespective of what it is. So that's what a hash function is. So it's a one-way hash. Okay, a one-way hash function must be pre-image resistant. We'll see what that means as we go on. These are some characteristics of a hash function. So second, pre-image resistance. We'll explain what this means. Just look at some of the properties of a hash function. We also have a secure cryptography, or we call it the ideal function. Must also be pre-image resistant, second pre-image resistant, and collision resistant. That one, collision, is very important. Now, in Bitcoin, it uses two types of hashes. It has the SHA-256 and the RIP-MED 160. Remember again, when we say it has this, we are saying that SHA-256, we have different types of hashing functions, okay? You have the MD5, the MD1, the MD5, there are a range of them, but right now, what is being used is the SHA-256 and the RIP-MED 164 in the Bitcoin blockchain. That's what's being used. It started out with the early ones, where you have the MD1, later went to the MD2. What matters in a hash function is when you pass data through it for a regular hash function. Let me go back to that image we saw previously. When you pass a function to it, any data to a hash function, a normal one-way hash function, it produces this fingerprint for you. It doesn't care what the input was. All it does is it gives you that fingerprint, okay? And normally, it's in a one-way stuff. You cannot, from the fingerprint, guess what the original data is. No, it's a one-way thing. It just goes in, creates a hash for you. All you can do is to verify that, okay, this thing is what it is. All right. Okay. So there are different applications of this. One major one is the hash table. I work with this one a lot. The hash table. So let's say you have data. Let me use this course, for example. Let's say we have all the 31,000 students, all right? is data. Now, if you're writing a computer program to look for something, there are different algorithms, of course, you could use to search things, okay? But one thing with the hash table, it makes your computation quite faster. And here's how it works. So I create a hash table. There's a way to create hash table, depending on the program the language you're doing, okay? So you make a hash table, and it's empty, there's nothing in the hash, you just create a hash table. So what a hash table does is, you give it some value. It makes a hash of that value. It's not that simple though, but you do what you call the mod division of it. So bottom line, it did some manipulation with that data you give it. Now, in the hash table you made, it will create different storage areas. Let me use language you can understand. So you come into a hash table, you have different, if you're used to cloud, you hear about buckets. When you say you want to use, let's say you're doing AWS, you have buckets where you store, it's a storage system where you store your data actually. So it just makes some, storage areas. Now, when it gets the value, it hashes that value. From the value it gets, you know exactly where to go and keep it, right? So it gets another one, it hashes that one, does all the mathematical thing it has to do, it works out where it should be. Now, when you are looking for a data and I say, okay, I want to get this data. So let's say I'm trying to go through a list of students, the 31,000 students. It's a lot. If you start going through all of them, you're searching for a name. Let's say Dan Gavas, or one of our students here, Haruna Dan Gavas, for example. I want to search for Haruna Dan Gavas. Okay, one thing can happen. I can go through all the data one by one, right? Okay, of course. And keep comparing until you find out, okay, this is what it is, right? Okay, this is another thing I could do so that I'll be faster. I don't have to, because, okay, let's say I finish with Dan Gavas, I get another name, I still have to go through all the 31,000 lists again to find out. So for each name I'm looking for, I have to go through all the lists. But if you bring a hash table, for example, all right, so I could just say, hey, get the first name, all right, then store it in a hash. So what it does, it gets the first name, makes a hash of it, it will check it goes to the hash table. You already know to where it's supposed to be. If it's empty, it will store it there, right? So if you get another name again, it just knows what it's stored. So when it's searching through, so the name you give it, you already know where it should be. So if I say Haruna Dangabas, it knows, oh, this guy should be in number, blah, 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 so bucket. You just go right there. So it's quite very fast, rather than do things 2 times, you can run through your list only once. And that's running through your list, you're creating all the entries in your hash. So that's one way. And you have digital signatures. You already know much about this, your private key, we know what happens with your private key, used to sign your transaction. So over there, hashing is involved, because when you look at it, all you see some bunch of numbers, some bunch of addresses, they've been, so using hash to mask whatever it is, it's not obvious to whoever looking at it. So we have one-way transformations. You might be writing a program that you want to transform something to another thing. So you can use hash, it hashes it, transform it to some other thing for you. And you can use the right keys. You want to make keys, for example. You can grab anything. One good thing about hash function, I think in the next slide, you can use it. You can use anything as input. Remember, we say bit stream. When we say bit stream, in the beginning of the slide, when we discuss what a hash function is, we say it's a process that maps a bit string of any length to a bit string of defined length. So it doesn't matter what it is, whether it's an image, whether it's a letter, everything. Remember, bit are just zeros and ones, right? So you can use anything whatsoever in doing your hash, to generate your keys, your indexes, sorry. So it accepts anything whatsoever, no matter what kind of data it is. Your hash function will accept it and give you an output that you want to use for something. So in the hash function, there are 2 fundamental uses of hash function. Number 1 is data integrity, and number 2 is data access and efficiency. I'll spend a little bit of time here to explain this. So what do you mean by data integrity? Let's see. So data integrity is the way you want to make sure that data has not been tampered with. All right. So you want to make sure, oh, I have a data, this data have not been tampered with. For example, when you download, if you go to the Debian, that's the Ubuntu, Ubuntu family of Debian. Ubuntu is one of the Debian family of Linux operating system. So when you download it, let's go to their website and see. I just kept this here for, I have a page I opened up for Debian. Let's see what happens here. 1 minute, please. Take this out of here. Okay. Let me zoom in on this. You come out. Okay. For example, if you go to the Debian website, so they have, this is an image, Debian 11.6.0 AMD, blah, blah, blah. So they gave the fingerprint for it. You see this 224, blah, 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 all these string up to 51. That's the fingerprint for this particular software here. Okay. So what happens here is if you download this software, for example, you download it to your computer. Before you use it, you want to make sure the data, this image is coming from the publisher. Because if the publisher told you, hey, we've done this image and look at the key, if you hash it, you'll get it. All right. So before you use this, you install on your machine, you use your program, you can have SHA-2. If you have a Mac or Linux system, you always have this SHA-256 stuff on it, right? So you can use it to check this software you downloaded, whether it will give you this fingerprint. So when you check it, I give you this exact data here. You know that this data is correct. Nothing has happened to it. Let me take an example here. No, not you. Okay, that. So here is the command for you to check. I'll run it on my machine maybe so we can see. So what I just explained there, you go to, Debian website, you want to download their software, you see where they put the checks on, you go there and you tell you that this Debian ISO image, here you just check some for it, the fingerprint. So after you download your stuff, you now run this command, open SSL *512 and sorry, I went back. Sorry about that. Okay, so this command I have here is in the material. If you have done this course on fifth, or you have seen this command already. Okay, I'll try to use locally on my machine now. The command is open SSL, then *512. Once you put those things in, you now pass whatever data you want to pass through it, and it will give you the fingerprint. So let me just use something on my local machine and test this. So for example, let me see. I have to zoom in on this also, so we can see my screen. And I close. Yeah, close that. Okay. Control plus. Just want to increase my font size. Okay. Almost set. So let me clear this screen. All right. So I just clear my screen. All right. So let me see what I have here on my machine. Hello.go. See the dot pwd. Where am I at? Okay, let me back out one more directory. Okay, great. So here in this directory, I have some of the courses we have done before. For example, Introduction to Golang Part 1. And let me look for something simple we can modify. You know what? Okay. I have a simple text here. Star dot. Let me look at this. I have one file here called star underscore input.txt. I think I just created it. So let's see how this works. So I want to see what's the content of that file. So let me cut it to my screen. Sorry. Not sure why this is slowing down so much. Not responding very well. Oh, okay. So cut that. Okay. So let me clear the screen just so we are clear. So let me do that again. So that file we just saw, look at the content. Add functions, map an arbitrary length input into a fixed length output. I picked this thing from the material on fifth work. So this is what it is. It's just a single line, and it says hash functions map an arbitrary length input to a fixed length output. So that's what it is. So let's hash it and see what it is. The command, I think, open SSL. Let me remember. Open. One minute. Open SSL. 256. Let me confirm the command, please. 1 minute. That one. Okay. *512. We are using *512 on this. Okay, that's fine. And I want it to take this text. Okay. So what I said open SSL *512. I pass this text, this file to it. You can take this file. This file could be a video. It could be a software, an ISO image. It could be anything. It could be a sensitive document. Okay. Now see the fingerprint. It started with 1B, 1B4, blah, 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 and ended with 6EE. Let's run it again and see. We have the same stuff, the same fingerprint. Remember what we said, you pass any data, whatever the data is, just pass it on to a hash function. It will give you a fixed length. It's the same length, no matter how long or short the document you pass into, it always give you a fixed length, like we just saw now. Okay. Now let's do something. Let me go back to that file and change one thing on that file. So what I'm going to do now, for simplicity reasons, let me just add something to it with my command. So I'll just say echo. Now don't worry about what I'm typing. All I'm trying to do, I want to put in more text on that file. We'll know when I finish, you'll see. So echo, I want to add added, let's just call it added text, right? And where I want to put it to, I want to redirect this and put it to that file. The name of the file is sha something something. Yeah, sha_info.txt. So what I just did here is the same thing as you opening the file physically and go and type something into it. I'm only using command to send into it. So it will just go at the end of the file, add this other, go to the next line and add this thing I just said. And the text is added text. Okay. Now hit enter. Okay. Let's see if it works. So how do we know? Let's run the SHA. Let's pass it through the SHA-512 again and see. Great. Now see what happened. I didn't open the file, but I know it has changed. The first time we run it, it stopped with 6EE. The second time we run, the second time is 6EE, is the same file. So if you run it 1 million times, it will give you the same fingerprint. That's what the hash function does. But the moment you change anything, even if it's a single dot, I added two words, added text. That's what I added to it. And we did it. Now look, I stopped with 14D4 and it started with 087. So it's not the same anymore. So it has changed. So when we say data integrity, this is one way you know that data has changed. Let's give a more practical example where this is very powerful. Take Nigeria election, for example, that just, we have the BVAS machines. The BVAS machine, they were used at the polling units. Okay, they were the primary source of data, everything in it. And then after the whole, so people were like, oh no, it seems something was, allegation, allegedly, it's not us to say that, oh, it wasn't, things didn't tally up. And so you say, okay, give us access to the BVAS. Let's take a look at it. So me as a computer science guy, not computer science, just as a tech person, the first thing you want to do is to make a clone. Yeah. And we have some tools that are forensic tools used to make a clone. When you clone, cloning is different from backup. Let me give you the difference now. If you want to back up a data, if I have a data in my machine, I can say, okay, there are backup programs. Okay, back this program up to somewhere, all right? So it grabs that program, takes it to another location, and writes it there. Now, as it's writing that program, it will introduce some metadata. Metadata means data about what you just wrote. For example, there will be a timestamp, all right? Let's say the election happened on the 25th of February, for example, and you do backup on the 29th, maybe. So it will have a metadata that said it was 29, all right? Now, that extra metadata, and sometimes when you're doing some backups, some other bits are also written together with the backup. So you find out that the backup you did, it's not the exact stuff on the machine. But if you make a clone using the software tools, the forensic tools, when you clone it, it gives you the image, so image of that machine. Now, what can you do with it? You can now run that image. The image is a file. Someone will saw the ISO.is, it's an image. So you make a hash of that image. It gives you a unique key, all right? You store that key in a blockchain. That's it. So when you now want to make analysis, of course, you make more than one clone, because that clone, you can't work with the clone. If you open up that clone and close it back, you might have introduced a data. And that extra bit you introduce, if you do another hash, it's no more the same, it has changed. That's why in lockout most time, when you're making a video, they'll ask you to bring the device from which it was, the video or the photo or whatever, bring the device with which you did the original, the primary record, the primary recording device. When you bring it and you make a clone of it, you can continue. So hash is very powerful. There is one company, very big global, not a very global company, and what they do with their machine, maybe when they are done with, they are going to close down from work. They make a hash of all their machines, of all the data in their machines, right? And store that hash on the blockchain. So when they come back the next day, you also make a hash of those images again, those data. If they're the same thing, that data has not been tampered with. So you can work with it. So hash is you can see how powerful it is. It can solve big problem if it's applied very well. And why do you store on the blockchain? For simple reason. Once you store on the blockchain, remember you cannot
change that. You cannot erase that, okay? And so when you come, you see the timestamp and everything. Okay, the same string. And you might even say, okay, we are storing in the database. We want multi-signature. Not just me. Let's say the owner of the data will sign. Me that's trying to scrutinize the data will sign. And maybe another third party will sign. So we'll have 3 signatures. We'll get to that when we'll go multi-signature. You can have, when you have your script, you can give the condition under which that script will come to true. You could say multi-sig. You require 5 people to sign, but out of that 5, any 3 can sign and it will be valid. So you might have 5 parties, all of them have signature. Once 3 of them sign with their keys, it becomes valid. Once it's true, the transaction will go to completion. So that's how powerful the hashing thing is. Pass any data to it, pass any media to it. So if you're doing this program, if you want to, one way you want to make sure that somebody didn't tamper with the data is to do a hash of that data and keep. Imagine if you're a writer or you want to make a review and the document is 1,000 pages, maybe even 5,000 pages. Come on. All right. I'm talking of soft copy, digital data now, 5,000 pages. And you want to know, have something change in this? Did anybody change this document? It's simple. That original one you have, that 5,000, just make a hash of it. It give you the fingerprint. That's it. All right. So whenever you get another one, say this is the same copy, because I might come and remove these 2 letters, IS, and put SI. You still have the same length, but data has changed. So when you run another, when you run into a hash, that one that has changed figure or any, have changed a character, this fingerprint will be different, and okay. So that's what we mean when we say that the hash, one of the major uses of hashing is for data integrity. So as students of this course, some of you already are saying you want to work on things that have to do with the election. We've been seeing your project ideas. They are wonderful, wonderful. And like if you were in the class, the last one we had with the BSV team, I told them to give us their final words, and they gave 3 things, and I still remember them vividly. Todd, I think it's Todd. Todd said you have to work in groups. That's what Todd said, and that's correct. That's why we say, you guys, this project we are doing is not a one-man project. We can't just bring one person and do one person's project. We don't have resources for that. So the project will happen in groups, right? Where you work, because one person can't solve it all. I keep saying this, some people have criticized and say, hey, you people are too lenient. You allowed people to continue. Yes, we did. We allowed as much people to continue because we understand what diversity is about this course, right? So we want to train as many people as possible. So whatever the barrier is, we try to lower the barrier to bring in a lot of people. So because you have different talents. So in a group work, everybody brings their talent and you form something, right? And the other guy, the guy from Fitwell, Nicola Blaine, he said he doesn't know the problem of Nigeria, but we know the problem of Nigeria. So we should solve the problems of Nigeria, and that's it. So we have issue we are still battling with, and we will try to focus on those problems that addresses the Nigerian problem. Yeah, your problem can solve other people's problem, maybe global market, fine, but we want to first indigenize it for Nigeria, all right? Because there are other countries that have the same problem we have in Nigeria. Maybe when they now start doing blockchain, those countries, you already have the solution working in Nigeria. And the normal thing is, if you want to make something like that, you go and study how do people do it. So they could be the one coming to your company. If you are set up a startup there and say, hey, how do you do it? They might hire you to come and be a professional, towards their own project. So we want to solve Nigerian problem that are indigenous to ourselves. All right. Then Ivan now said, yes, he said, solve your problem that even though you didn't conclude everything, one thing with project, let me tell you this, if you know anything about biology or biotechnology, there's this tool they call CRISPR. What CRISPR does is they use it to edit genes, just like you have a Word document. You say, oh, you put dark somewhere. Say, I want to change the dark to fair. You go remove dark and type fair. So CRISPR allow you, there could be a gene. Let's say breast cancer runs in the family, it's genetic. Everybody inherits it. Okay. Oh, we found you do a DNA sequencing. So you have breast cancer in your family. So you can bring CRISPR, go into your genome, into the genome, cut out that part that codes for breast cancer, replace it with one that doesn't code for breast cancer. But do you know how it came about? Somebody was working on bacteria. They find that there's some bacteria that they have some memory. Once a virus have attacked them before, they somehow, whenever that virus come attack them and they survive it, whenever the virus come to attack them again, it doesn't do them anything. How did they do it? So they were trying to solve a problem of bacteria, and they cracked something and formed CRISPR that now you can use to do editing in mammals, in animals, not just bacteria anymore. And they won a Nobel Prize for that. So in this project, let's look at the low-hanging fruits, things that are very common to us, that are issue right now, which you can see the BSV team, they say they will pay more attention to low-hanging fruits, and they're good for us, okay? So as we are trying to solve the low-hanging fruits, something might come up and your same solution will go for that, right? That's just a diversion from the course, but I think I needed to say this over here. Okay, so that's what happens with hash function. You can use them to ensure data integrity. I think I explained that vividly enough for us to understand what we're saying. The next thing is hash function is used for efficient data storage and retrieval. Yes. Now think about this. You have efficient data structure. Let's say you have a document. It's, I don't know, let's say 5 gigabytes of data, for example. That's a lot, that's huge. Now, it's not efficient, it's not efficient to take that 5 gigabytes and store on the blockchain. Think about that. 5 gigabytes, it's a lot. Okay. Yeah, you can store it, but remember, when we start doing transactions, we find that during transaction, the cost, what you are actually charged, is not a function of how much digital cash you are trying to send. No, whether you're trying to sell 1 million digital cash or one digital, it doesn't matter. What matters is what is the size of the data you are trying to validate. So data, the size matters a lot. If you have a transaction that has plenty UTXOs, unspent transaction output, plenty UTXOs, the charge for that will mirror the number of UTXOs you have. All right, you can have one single UTXO that have high value. It's cheaper for you than having, gather small UTXOs that form that same value. So rather than store 5 gig on the blockchain, you take that 5 gigabytes and store it on like IPFS server, interplanetary file system. What it does is it's a decentralized method of storage. So when you store it on IPFS, it doesn't stay on one computer. The bits get scattered around through all the competing computers in the node. So even if 20 computers are not online, it doesn't matter. It gets it. Oh, there's a good example of this. BitTorrent. The torrent where you want to download file from a BitTorrent. What actually happens? There's no one single machine that has having you that file. What it does, we call seeding. Look for all the computers on the network that were active that has that file. So it starts getting them from, it starts seeding from those machines. Sometimes you see the seed is plenty, after a while it shrinks. Maybe some computer gets shut down. The owner say, hey, don't seed anymore. All right. So something like that. So you take the 5 gigabytes, store it in IPFS server. But before you store that, you do what? You make your hash. So that hash, anyway, the IPFS will make a hash for you anyway. So you take the hash and now store in on the blockchain. And what is that hash? 256 bits, 256 bits. That's about 64 bytes. All right. So 5 gigabytes, but what you're actually storing is just 256 bytes, 250. If you're using SHA-256, you're only storing 256 bits. See how efficient it becomes. You know, you don't need to put the whole large data on the blockchain. So that digest, it makes storage very easy, efficient, and retrieval is also very easy. You know why? When you are trying to retrieve from a hash, anything stored in a hash table, for example, all it does, like I said before, it does a hash of whatever you want to do. It knows exactly where it is. It goes there and put it up for you. Now, the previous hashes, some of you, if you have read through, you should have read through the document. You see the MD1. What was the major flaw of MD1? And the major flaw was that after it was, from MD1, they went MD2 immediately anyway. But even the MD2, the major flaw was that as computer became more powerful, okay, I've not thought about collision. So we get to collision. When I get to collision, in fact, 1 minute, let me pull up the cost material. 1 minute, please. Here is it, fifth one. Okay. Okay. Here. Okay. So in the material, there was an example of to compare what happens with array. Array is another data structure. Let me say the hash is a data structure in computer science, you know. It's very efficient. In fact, most other data structure, you can use hash to develop other data structures. You should know that when we say data structure, you can form your own data structure. If you can find an efficient way to do stuff, you can write your own data structure and implement it. It works. In any language you can implement your own. So if you use array, is other one, yes. If you use an array, for example, to store data, what it does, an array is a data structure, but what it does, it has an index. So you need to locate what's the index. You just get the first index. After writing, it takes the next one. So the memory is contiguous. It doesn't jump. So once you get the first index, you can get the 10th one by just moving 10 places. You know, so when I say index, I'm talking of memory storage. So when you make an array, for example, it goes and creates, let's say you make an array of 50 storage units. And when I say storage, I mean, it could be, if you're using integer, for example, and you say 50 int, an integer use 4 bytes. So if you do 50 times 4, that's 200 bytes. So if you declare an array of 50 integer, it will make provision for 200 bytes for you, because each integer will take 4 bytes, just like that. So if I know where is the starting point, we call the index. If I know the index, you can locate any other thing, because you know from the index, the second one will be after 4 bytes, you get the second one. After under 4 bytes, you get the other one. So you can calculate. So you know exactly where it is. But one thing with the array is everything will be in sequential. So let's look at this program together. I'll zoom in on this. Okay. So I already have this. I put it up in my. Okay, let's read from here though. So we know what package means. Oh, this is, by the way, this is Go. Some of you are asking me, when are we going to use Go? Well, you already know we're using Go right now, yeah? So we've done this already. In every Go program, you must have a package main, right? Then you have to import your libraries. We'll see along the line. We are used to this FMP, the format. As we go along, you see, you can write your own library, import it, it will behave the way you want it to behave. So variable array, you just declare a variable called array. And how do we know it's an array? Because of this square here. And this array stores string, right? let me open up this in my VS Code. Do I have hash functions? Yes. BB arrays, yes. Okay, ls. Let me clear this place. Okay, so I have the array here. Oh, so I just open it up here. Here is it. So I have to close this for now. Let me see. Okay, here we are. So that's the program. I already put it up here when I was preparing for this lecture. So we import our FMT, and here is function main. Remember what we say function main, that's the entry point. So if you can have so many functions, it's okay. You can declare all of them in the top here. Declare all your functions. If you process them, no problem. But once you want to run the program, it will start to run from the main package. That's why if you don't have a main package, it will throw an error, or it will tell you, hey, there's no main package. Now let's see what we have. We have a variable called array. And this array is an array. What makes it an array is not because we call it array. You can call it anything. What makes it an array is we have the square bracket here, and we put 10. So we are storing 10, we are reserving 10 positions for it. And what kind of data will this array store? It's a string. That's it. So, and this is equal to, here is our string. It returns a string. So you are initializing this array, okay? It's a string of 10, and whatever it returns will be a string. And inside, what do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 values in it. Okay, now we run a function. This is a loop for I equal to 0 to I less than 9. Less than 9, yeah? We have our increment here. So what we're going to do is say print %s means it's a string, print a string. And what are you going to bring? Array. Now, in array, you access an array with its index. So index I, we stay from I equals 0. So in the first time, I will be 0 here. Here we have I, it will be 0. So it will print whatever is in array 0, which case is array 0 here is 1. It goes back, it checks, is I less than 9? No. Yeah, it's less than 9, so it continues. It does 2, it does 3, it does 4. It continues until it does 9. It comes back again. Is 9 less than 9? No. So it stops. I'm not sure why they did it. This is that code we have on the material. They did it in two places, but that's fine. So from here we print to you 0 to 9. That's what, because after printing 9, if you come back, 9 is not less than 9, so it won't print another one. Remember, we have 10 here. Okay. So this last one now say print array index number 9. Remember, arrays are 0 index. So you say index number 9, we are talking of the 10th element. Remember, because the first one is 0, 1, 2, 3. So index 9 is the 10th element. Index 0 is the first. Index 1 is the second. So index 9 is the 10th element. So we could actually have said here, anyway, let me run this code and see first. This is supposed to be our output. So let's go ahead and run it and see what we got. So I'll just say, go run that, yeah? Okay, I say, go run, what's the name again? Array, yeah, .go. Okay, see what we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you know why we have the 10 here? Because of the, if I comment this out, for example, this second fmt.print, if we comment it out, Oh, I've not saved that, did I? Control S. Okay, yes. So I commented I will now have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it was this second one that printed a 10, but we could have just changed this value here for I less than 10 instead of 9. Sorry, less than 10. If I put I less than 10 here, then we don't need this second print here. And I think we'll get, in that case, yeah. Oh, I see why they did that. Okay. It makes sense now. So sometimes you have to, let me tell you why they did that. Let me run it before I tell you. So let me run this same code and see what happens. So it gives us 10 again. You see, it did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is what we had before. But see the problem now. My prompt continued from the first line. So either way, you need to, I can just say print only, n, new line character. So they just wanted to introduce a new line character so that the carry return goes to the next one. So I see why they have this, they left it at 9. And then put this back on. So if you watch here, you see there's after dollars, after the string, you have percent backslash n means make a new line. So what it's saying, after printing the last one, give me a carriage return, go to the next line. And that's why if I run it again now, we'll have, yes, 1 to 10, and my prompt starts from the next line. So it's fine. I'm not going to mess around with the code. It's okay like that. Now, what we are trying to show here is, look at the output. It's sequential. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got that, right? Because that's how we see, how do we thought it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's how we saw that. We got it like that. That's for an array, but in a hash. Now, hash does its own storage by looking at the input, whatever value what you're giving to him on a hash. It does all the manipulation it has to do. It will know which bucket, where exactly am I supposed to put this. So it gives you something that's random. It's a longer code. Let me go back to the main page. I will just explain it and we move on. So here we have it. Now, but look at the difference with the hash. Now, the hash is a more longer stuff, but this is interesting. Let me highlight this place for you guys. Look, we'll be working only with FMT, the format. Now we're importing more. We're importing byte. Now, this is a library. It's a library of its own, right? A kind of a function anyway that has some functionality. So we're trying to use that. They are standard on with C, with Go. And we import this one, encoding binary, right? And there's another library that has to do with Go -BK. And we brought the math-B. So all these are needed for this code to work. And this is how you write your own. So you can write your own package and import it, then you use it anywhere. So in this case, we're making what we call a struct. This is how a function looks like. We use a struct. So the type cell is a struct. We call it a type, and here we give it a name called cell. And it has certain attributes. It takes a key, and this key is a string. It takes a value, so key value pair, and the value is a string. Then it has a pointer. Next. So next is a pointer to a cell, which is the next cell. So you start from somewhere you want to keep track. Remember, in array, if I know the index, I know every other thing. I know the next one is here. I know where the next one is. The next two, I know where they are because they are contiguous. They don't. That once you see I0, I1, it's contiguous like that. That's how arrays store. But for this, it's not contiguous like that because when you hash a value, the bucket might be number 17. You go and put in number 17, the first value. You hash the second value, which is 2, for example. The bucket might be in number 1. You go and put it there. So it's not contiguous. That's why they introduce a pointer. That's why there's a pointer here. You need to keep track. If I know the first, where is the next cell? If you tell you where the next cell is, so you need to keep track of it. That's why you have a star. This star means it's a pointer. Pointer, what pointer does? Pointer stores an address to a particular memory location. So if that address is bucket number 18, so the next, if we saw bucket number 18, not the value, but the address is bucket number 18. So whenever you go to bucket number 18, whatever you see there, you take it, right? So I was saying something about the MD2 before. So one major flaw the MD2 had then was they found out what we call collision. Oh, it's still down there. I'll mention collision down the line, but I could just say this. So collision is for what collision means is, okay, you hash a value, give you bucket number 17. That is possible. Also, along the line somewhere, someday, you hash another value. If we give you bucket number 17, now that's collision. Remember, you already have something. So you having two values resolved to the same memory location is not good. It's not a good hashing algorithm. So hashing algorithm try to prevent that. That's why you have, so MD2 failed that when they found out, that's why we have other types coming up, all right? Because with MD2, you can change it. You can just make another value, replace what was there before and change by. So data integrity will be a problem. Okay, so that's, it defines a cell. A cell has key, value, and next. Those are the things. Now, there's another type called the hash table. Now, the name hash table doesn't make it a hash table. It's just a name. You're naming it so you understand, it makes sense to you doing it. Because you call it hash table doesn't make it a hash table. Okay. Okay, we call cells. That's a new stuff. So inside hash table, we have cells. We haven't defined cells before. We've talked about cells. And what is a cell? Cell is an array. It's a pointer, it's an array, okay, of cell we defined before. You can see it's a pointer. That's what it is, to an array. And I defined this cell before here. Okay, so cell is an array, okay, that points to a cell. That's what the cell is. So whenever you call a hash table will have many cells. That's the bucket 1, bucket 2, bucket 3, all those things. So you create them from here. And now function main, we know what main does. The reprogram starts. So you see the hash table, you make a new, I'm not sure this, okay. You put a new hash table is a function. Let me see if it's here. I must be defined somewhere else. Okay, no, so I guess this is a mistake. I've not run this program on my machine, but new, then hash table. Maybe if you have run this program, let me know if you had a mistake there. If there is, because we don't have it. It's just making a new hash table. But let's see. 1 minute, hash table, new hash table. I don't think there's a function new hash table here. No, I don't think. So just in case you have a mistake, please go and take a look at that place. New, I think we should have hash table. Either you have new space, hash table, something like that. So here we have now hash table.insert, index 0, whatever that index you put 0, insert index 1, that, blah, 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 blah. Now see what's going on here. We start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now see, we start 0 in index 0, 1 index 1, 2 in that. We created these indices for all these values. Now, if this is an array, if you print it, they will be sequential. But all we are trying to show here is the last part here. Let me go down. Let's not bog down with. See what we're trying to say. When this program was run, finally, look at the values. Output was 3, 4, 5, 9, 8, 0, 6, 7, 1, 2. Have you seen the difference? In the case of array, it's contiguous. Once you have 1, the next one is 2 and 3 and 4. It's contiguous the way you inserted them. Let me go back to this one here. Look where we inserted this, where we put the value. We said 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when we printed this, we had 1, 2, 3, 4, it followed the same way. Now look at for hash. So our index 0, we saw 0, index 1, but when we run it, you see that the order is random. Like I told, so when you run the first one, which is 0, it didn't go and put it in the first bucket. No, because that 0 has to, let's say 1, 2, 3, 4, 5, 6, to the 6th bucket. So you go to 6 and put it. So anytime it sees, if you make another thing that is 0, you already know where it should be. You see how it is. And that's why they came out like this. So that's what we're trying to show here. For array, they're all contiguous. For this other guy, the hash table is not contiguous, okay? It's random. That's the word. It's random. It depends on where it should be. So that the first thing is the first one, the second one doesn't mean data are stored like that. No, it will make a hash of that and go where it should be and put it there. And that's why it's a very good data structure. You can use to build so many other stuff. Okay. That's what you say. Notice the output of the hash table is not in order like arrays. And that's because the index of values is determined by the hash of each key. You see? This is what makes hash table so efficient, because the index of the values is provided when fetching the data. So retrieval is fast. Yet, almost any kind of input can be used to derive the index. I remember I would say you can use anything. You can use image. You can use an image you can use an NFT to generate an index, anything at all. So it makes it super, super nice, right? Okay, look at Merkle trees. There's a full course on Merkle trees, so we'll just brush by. It's part of the course here, so we'll look at it and we'll go by. So Merkle tree is another data structure, and this is what you use when you have all your nodes, all right? All your not nodes, sorry, the ledgers, the blocks, the blocks as the block growth. So let's go and see what happened. Let's start from the base. So here's a data set. You have A, B, C, D, blah, blah, up to P, all right? So this is a block A, block B, whatever it is. And remember, in block, you have so many data. You have the index, you have the block height, you have the nouns, the number used once, you have the bytes, number of bytes, you have so there are so many things you have. We call the block header, okay? So you can see here, you have your HA and HB, okay, the header A and the header B, okay? So we could make a hash of this and have our HA, and make a hash of B and have our HB, okay? Now, when you make a hash of both the hashes of A and HB, you now have HAB. So see what we're only storing hashes now. Data has been there. You remember, once you have your hash, you have a key. So the hashes we are storing, the digest, that's what we are storing here. So for HA and HB, you have this. So if I know this key, for example, HAB, if I know the fingerprint, if I come and do something and compare it with this HAB, if it's the same, I don't need to come and check what is A and B. Because if I make a hash of whatever data I want to verify, and it's equal to the hash in HAB, it's telling me that the data here hasn't been tampered with, they are accurate. You see that? Now we have HC, HD. When you have the two of them, you have HC and D. Now you have HAB and HCD together, and you have another hash here, another fingerprint stored here. So if I want to do verification, for example, and I get to this place, HABCD, and I know what the inputs are, if I hash them and they're equal to this one, I don't need to go study what is inside here because I know it's correct. But if I hash them, it's not correct, oh, that's a problem somewhere. You see that? So same way, so it grows like that. It forms what you call a tree. If you look at it, that's why there's an image of a tree here, where you have roots. This is the root. That's called the Merkle root. Merkle, yeah. How do they put it? Yeah, in recognition of the person that developed it, Merkle. So, but it's a root. So it's like this. It has two roots here. This one, each of them have a twin. So we call this leaves. Each of the node. If I use this, here is a node, for example, not in terms of computer node. I'm talking in terms of data structure, we call nodes. So in this node, you have two leaves, okay? Two child, or we call them children. This particular one has two children, this and that. Then this one here has another children, this and that. That's until the final one here, these are the leaves, the HA, HB, they're all single leaves like that, okay? So now this HABCD is a grandchild to the main root, because this is a direct child, this was a grandchild, and this was a great grandchild, and this is great grandchildren. So something like that. But look at the beauty of this. Let's say this is numbers. That's the way you store data on a Merkle tree, for example. Well, this is what we call the binary tree, actually. And you know why it's binary? Each node has two binary. Each node has two children. You see that? So binary tree, that's what it is. And look at how it's efficient. If I'm trying to look for a data here, for example, 1 minute, let me look at the comment section. I hope you guys hear what I'm saying. Let me see. Okay, yes, no complaints. Okay, good. All right, getting back to the slides, or rather to the, yes, okay. So see how you store data. Let's give you a simple example. If I want to store data on this, for example, all right, let's say I start with the first data is 2. I put 2 here, so 2. Now I bring the second data. Can I make a screenshot of this? Let me see. I make a screenshot of this. Yeah. I just need this one, actually, only this far. Okay, I'll bring this into, let me add a new slide here. And just bring that in. Okay. Uploads. 1 minute, please. Let me bring this in just so I can write over it. You could see. Oh, here it is. Upload file. 1 minute. It's coming. Okay, here it is. Coming up. So yeah, put that here. Okay. Zooming on this. Okay. So let's say we have numbers. Text. There it is. Okay. So let's say inside here I have, let's say, 6, for example. Let me start with 6. Oops, sorry. It's not you. Yeah, that one. So let's say the first one, we have 6 here. Okay. Now, or let's make a sequence. Control C, Control V. Okay. Let's have a sequence of numbers. 6. Do I say 2? Do I say 4? Do I say 1? Do I say 7? Let's say 9. Let's say 13. Okay, 23. I'll leave it like that. And let's say 5. Okay. So these are sequence of numbers we want to store. So the first one is 6. I put 6. Okay. The second one is 2. So let me remember. Yes. So 2, I'll say is 2 bigger than 6 or less? 2 is less than 6. So I'll store it on the left-hand side, which means my next figure now, Control C, let's copy this, Control V. So I'll store 2 here, change this to 2. So this is my 2, right? What's the next number? The number. I'm sorry, I lost connection temporarily, but I think I'm back. So I'll have to share my screen again, I guess. Let's see. Okay. I think I was sharing my whole desktop earlier. Yeah. Okay, I hope it's shared now. Let me minimize this. Okay, so I'll just be fast on this. So what I'm trying to say, the next number here is 4. 4 is less than 6. So I come to this side. It's 2. Now, 4 is greater than 2. So I'll store it in the right-hand side. So which means the next data comes here. Control V. I'll move the next one here, which is 4. I have 4 here. Okay, the next one is 1. 1 is less than 6. So I go to the left-hand side here. Now I have 2. 1 is less than 2. So I go to the left of 2. So we'll put 1 here. I copy this, Control C, V, and come here. And this will be my 1. Yes. So okay, there's a pattern. This is 7. 7 is greater than 6. So I won't go this way. I'll come to the right. So I can store 7 here. Control V. Copy this again. Put here. This thing, we have 7 now. We have 7, right? The next number is 9. 9 is greater than 6, right? So I'll come to the right-hand side. I have 7. Now 9 is greater than 7. I'll go to the right-hand side again. So I'll put 9 here. Control C. And V that. Put here 9. 9. Now 23. 23 is greater than 6. So I come to the right-hand side. I have 7, right? 23 is greater than 7, right? So I come to the right-hand side again. I have 9. 23 is greater than 9, so I come to the right-hand side. I can now put 23 here. So 23 stays here. I'll stop at this and make the analysis, 23. Now, see what's going on. We are storing this data systematically. So what it means, let's say I'm looking for, I need to go one more step. Let's add 0 so that it makes sense a bit. Let me add 0 to this list. So let's have 0 here, 0. Okay. Okay. So let's put 0 to the list. 0 is less than 6. So I come to the left-hand side. We have 2. 0 is less than 2. We come here. We have 1. 0 is less than 1, we go to the right. So here we have 0. I'm supposed to put 0 here. So CV. Okay, I have 0 here. Okay, now see what's going on. So let's say we want to look for 0. I'm searching for 0. See how easy it is. So I'll just look at the first one here. It's 6. I know that 0 is less than 6, so it should be to the left-hand side. I'll move down here. Do you know what I've done? We have cut off the whole of this. We are not going to search all of this. It's gone. So we're only on this part. I come here, I see 2. Now, 0 is less than 2. I'll move to this side. You know what it means? We're not going to search all these ones again. They are off. Now, 0 is less than 1. So I come to this side. So in effect, I only search 1, 2, 3, 4, and I've seen my value. Meanwhile, we have so many, so I don't have to go through all this. So this is what we have in the binary tree. This is an implementation of the binary tree. So it cuts your problem by half every time you try to do that. So it's very fast. Let me show you the graph for this. Try to compare it with, I saw a graph, I looked up a graph. Oh, I think this is this. Let me see. Yes. Okay, look at this. So the binary tree we just did, the time complexity is called log n. And this is the graph of log n. I will explain what it means in a bit. Now, this is log n. See how straight it is? Linear, it's a linear function. The more number you have, the more time it will take, which makes sense. If you have 1,000 different values, you have to go through at least 1,000. No, you at most, you can go up to 1. Let's say you are looking for 0 in a number of 1,000, and 0 is the last element. So you have to move all through the 1,000 elements one by one before you get to 0. That's why it's linear. The more the data, the more the time it takes. For n over 2, it's a little bit better than this. But look at log n, which is the complexity for Merkle tree. Let me explain what's going on here. In this part, in the horizontal axis, it says size of the problem. As you go away from the origin here, the problem increases. And this is the time you use to solve the problem. So as you go up away from the origin, the time increases. So let's say the problem was here. Let's say, look at my arrow if you can see it. Here I have, let's call it 1, unit 1. Let's go up and see. It hits here. It took this time. So initially, the time is almost the same. Okay? But let's move a bit. Let's say the problem grew by, let's say, I don't know, 6. For log n, no, for n, for a linear situation, the red one, let's go to the red one. Let's keep going until we hit. I couldn't even hit it. So let's use the lower one. See, for this, if I do this 0 to 10, here might be 8. So for a problem that is 2, it took me 8 minutes, for example, assuming it's in minutes to do it. Okay. Now, when the problem increased up till, let's say, 10, for log n, it took me barely 4 minutes. So you see how fast it is. Sorry if you don't understand graph. This is an image. I'm not really writing over it. I will make some sketches. But what I'm trying to say is that for log n, as the problem grows, the time does not grow. So if you have 1,000 values, it doesn't take you the time like 1,000 times to go through it. No, it takes less. You see, as you're going, it's almost approaching a maximum even, an asymptote sort of. It's approaching a limiting point, you see? So that's what happened when we did it. We look at the Merkle tree here. Let me pull that up again. I think it's here. Yes. Remember, oh, okay. I have it in the slide here. Remember how we did this now? To find 0, I didn't have to go. I just did 1, 2, 3, 4 steps, and I found it. So imagine that this is so large. So it's an efficient storage. And what you do mainly, you just compare the hashes. So if if I'm at this stage and I have all my transactions, I hash them. Remember, in a blockchain node, you as a node, you have all the transactions. A full node has all the transactions, okay? You can prune, you can say I want from so to cut space. But for transactions that you have, you want to validate, you can gather everything that has happened before up to this point. Once you make your hash and it's the same thing, you can assume everything here is okay. And you don't have to go to that. You see how fast it becomes. So it's an efficient storage. Why? Because we start using hash function. From hash function, you can use it to, in the Merkle tree, we use the hash function to construct the Merkle tree. The Merkle root, which is a very efficient way of storing data. Okay, so let me just read through this. So a Merkle tree is a binary structure, meaning its branches terminate in two nodes that's made entirely of hashes. So for example, the leaf nodes at the bottom of the layer trees used in Bitcoin are hash values of raw data from Bitcoin. So the raw data, when you hash all those raw data, it gives you those leaves we saw. And the successive layers of the tree leading back to the root node are constructed by concatenating the two hashes from the previous layer and hashing them together to form a new hash. This has the effect of connecting trees together to be represented securely by one single node, root node value. This structure makes it easy to find data at the bottom of the tree. And as well, proves specific data exists in a tree, which is particularly important for scaling the Bitcoin efficiency. Yeah, for scaling, at some point, you don't want to prove that this data exists without coming to that data, because if the hash here is fine, then everything down here is also fine. So that's it about the Merkle tree. Okay, 5 more minutes. We'll look at. So digital structure also is a course of its own. We're going to do it as a course. After this hash, we're going to do Merkle tree, then look at digital signature. Okay. So although the hash tables in data structure and Merkle trees are where hash functions have their greatest use, the most widely recognized use of hash function is in cryptography, in addition to encryption and key exchange. So we also use hash function in cryptography, in the digital keys, right? So for this one, we'll look at it in details when we go to study that. Okay, before we go, we should look at this, the major difference between hashing and encryption. So let's see. Let me zoom out a bit. Okay. So here's the difference between the hashing and the encryption. So on the encryption, you have a plain text. You encrypt the text, but you have to decrypt it. So this is a case whereby you are passing data to somebody, but you don't want someone to read the data. So you encrypt. You know what encryption means. You mask whatever it is. There are so many different types of encryption. We will see along the course. All right. So you have the base 64. You have there are so many of them. So you can develop your own encryption method. I have some C program I've written you can use to do encryption. Yes. So you can develop your own. Bottom line is you get the text, you encrypt it differently. You could say that 0 becomes 1, 1 becomes whatever. You decide what you want to do, right? And then you form your encryption. Now, when the person gets it, the key from that person will be able to decrypt it. So it's only the person that's meant for can decrypt. So in encryption, you have a plain text encrypted and you recover the text at the end of the day. But in a hash algorithm, you have a plain text. Now you hash it and you have a distinct, unique key or digest. That's the difference. So in encryption, at the end of the day, you get back your data. You want the person to see the data. But for hash, you are not interested in the data. You're interested in the key, that the representation of that data, the fingerprint of the data. So your job for encryption is just to generate a data that can give you that key. That's all. Once you get that data, it gives you the key. And that's what happens. So that's the major difference there. encryption. At the end of the day, you want to get back your data, but for the other one, you don't care. Okay, see here. So it says that number one, hash functions don't care about data loss. They don't care about data loss. All they know is we want the fingerprint for that data. Because for a hash function, you don't need the data anymore. It's not transmitted with anything. Only your own job is to generate another data that will give you that same hash key. And that's what happened in mining. They gave you the difficulty level. This is the level. So go and find something that's lower or equal to that level. So you must do permutation. There's no formula. You can't use the formula to mine. There's no formula you do and you mine. No, it has to be trial and error. So you have to keep increasing your nonce until you get something that is lower or equal to the difficulty level. And that nonce is part of what you put in your header because you use it for verification. When someone wants to verify, you take your nonce and see whether it gave you that. If it does, that's how also they verify. You see how easy these things are, the way the Bitcoin network was structured. So it has also produced a unique fixed length of clear text because it's nothing more than a unique digital fingerprint, and data loss is not a concern. But encryption encodes and preserves input message. So in encryption, the data is important because you want to pass that data on. Okay. So now hash functions are not reversible. That's a major part or a major property. If you can reverse a hash function, then it's no more. It becomes useless. So a hash function is a one-way function that does not need to be reversed. In fact, it's important it's not reversible. While in contrast, it's crucial that if you are encrypting anything, the end user must receive the actual message. So in encryption, message has to be reversed at the end of the day by decryption, right? So hash function has collision risk. Yeah, that's where we have problem, the collision. Remember, the hash, you only have a fixed length. It's a unique fixed length. Unlike in encryption, you have all the data, the entire data. So whenever you hash an entire data, you must have a unique key, cannot collide. Make sense? In hash, whatever you do, you have a unique fixed key that comes up. And that key, you still do other stuff with it. If you're trying to pop your hash table or anything, you have to do some stuff with it to get where you store your things. Okay. So a function has a collision risk due to the fixed length of the message digest. It's fixed. So it's possible for two different input values to produce the same digest. And Bitcoin uses hash function like SHA-256 and RIPMEX 160 because they greatly reduce the risk of collision. Yet, although their probability is insignificant, they can still theoretically happen. But in encryption, it preserves 100% of the text. So each encrypted message produces a unique output, and there's no collision. You can't have collision because you have all the text complete. But for hash, you have a fixed length. So you might have 10,000 character inputs. You have just a fixed length output. So that's why that fixed length might not be able to, represent theoretically. This is theory. In real implementation of this, I think that's the next page talks about that. The probability that will happen is very, very remote. Very, very, very remote. Okay. So I think we'll stop it here today. I'll try and wrap up every other thing in the next class. So I just want to have 2 classes for the hash function and then other ones, two classes for them. We'll now spend more time on Bitcoin infrastructure. We're not going to run through this one because this one will end by April 10th. Keep that in mind. By April 10th, it should be coming to an end. This particular, the Merkle tree and, but the one for the Bitcoin infrastructure, that's the main thing. So we'll spend more time on that. We'll have to rush through this. So hopefully I'll see what our calendar looks like. It can be Thursday or Saturday, one of them. And I'll talk with Harrison will talk with mentors so we know what time that suits best. I'll just take a look at the comment section just in case. Remember, this is a revision I'm doing with you though, but let me see. Okay, nothing here. Good. And nothing here. okay, someone saying to me, this meetup isn't enough. Can we have remedial class after online session at our extent? Yes. Yusuf Adamu, please, you can have as many remedial classes as possible, especially as you already have people that understand this very well. And let me tell you, if meetup is also difficult, you can do virtual. Just in case, if your mentors want us, we can give your mentors access to, we can give them access to our Zoom. Yeah, we can. I think we can do that. I'll see if that is feasible. Oh, no, you might not use, must not use. You can use Google Meet. Google Meet is free. It doesn't require license. You can use it for free, right? So yes, Yusuf Adamu, that's the point of the whole meetup, the whole forming group. I expect you guys to go to. I've been some groups. I've seen some group already. Some people have even started making videos for them. So yeah, go through them. I'll just do this major run through. I just want to make sure that we run it through, that you understand this some point. But yeah, that doesn't prevent you guys from discuss that with your group, with your mentors, okay? Where can we learn about blockchain technology apart from meeting here? You already have, also somebody said, where can we learn about blockchain technology apart from meeting here and meeting our mentors? You have the course material. So I'm just reading from the course material, okay? So you have fifth work already. And if you have any issue, you can look it up. What did I look up today? I looked up something today while I was preparing for this. I can't remember what. I can't. Oh, I think I did. Let me show you this. I think it was ChatGPT. I'm not sure I saved that session. Yeah, there was something I wanted to check. I went straight to ChatGPT, right? And I asked ChatGPT about it, and it gave me all. So please, you can use that too, right? There are so many tools you can use. If there's something particular you quite don't, oh, no. See what I was trying to do? Yes, I remember now. I was trying, in the course, there's a link where you can do, we didn't get to that here, where you can calculate hashes. So I came here, I put all the hashes, and when I said calculate hash, it didn't calculate, right? I want it on base 58 check, but I didn't get an output. So I went and told this guy, ChatGPT, I said, hey, ChatGPT, convert this hex value, I put this to base 58. And ChatGPT not only did it, it showed me the step he used to do it. It did all the mod division. It did it. Let me see. I'm not sure why I didn't see. Let me look again. Didn't I save the session or what? I'm not sure why. I'm not sure why really. But so yeah, you could, if you have something confusing to you, I think ChatGPT, the free mode still works very well and gives you a lot. So I'm talking to this person that asks, this is not enough. Yeah, there are so many tools you can use, okay? And I advise you to please do them on your own. So you get to, by the time you discuss it with your peers, you understand it better, all right? Thank you for asking that question. Okay, I think that's it. So we'll communicate you, always look out for your Telegram channel. Visit your Telegram channel almost every day because we'll have more activities now. Something is cooking up. I've not discussed it with anybody yet. So, but just know that the BSV team, I'll just say, let me make the announcement. The BSV team, the ladies, in the their management, in the last session, we have all, it was all male that talked to us. There's the female also. And they're interested in seeing if they want to have meeting with the females. And that's good. All right. So it's something we want to get some data passed through them. And once they give us their calendar, I'll let you guys know. Yes. So we're gonna end this here. See you guys maybe Thursday or Saturday. We'll find out. You just always visit the Telegram channel, the main general group, so that